Right now, the oldest light in the universe is telling us something that our best theories say is impossible. It is a pattern so precise, so geometrically unlikely, and so stubbornly persistent across decades of increasingly powerful measurements, that the scientists who discovered it gave it a name that reflects how deeply it threatens everything we thought we understood about the cosmos. They called it the axis of evil. That name was not chosen for dramatic effect. It was chosen because of how much damage this discovery does to the mathematical foundations of modern cosmology. And in the years since it was first identified, instead of disappearing under better instruments and more careful analysis, the anomaly has only grown stronger. More data sets have confirmed it. More independent measurements have pointed toward the same direction. And the community of scientists who hoped it was a mistake is running out of explanations. To understand why this discovery is so unsettling, we have to start with an idea that has governed science for the past 4 centuries. It is not a complicated idea. In fact, it is one of the simplest and most intuitive assumptions in all of physics. It is called the Copernican principle, and it states there is nothing special about our location in the universe. When Nicholas Copernicus dethroned the Earth from the center of the solar system in the 16th century, he did more than just rearrange the planets. He introduced a philosophical revolution. The idea that humanity does not occupy a privileged position in the cosmos became the engine of modern science. We are not at the center of the solar system. The Sun is just one of roughly 200 billion stars in the Milky Way. The Milky Way is one of perhaps 2 trillion galaxies in the observable universe. Everything points away from us being special. Everything points toward us being utterly and completely unremarkable. This idea has a more formal name in physics. It is called isotropy. In a universe that is isotropic, if you look out far enough in any direction, the cosmos should look statistically identical. There should be no preferred axis, no cosmic north, no direction that looks fundamentally different from any other. The distribution of matter, the temperature of ancient light, the motion of galaxies at the largest scales should all be smooth and featureless when averaged over large enough distances. This is not merely a philosophical preference, it is a structural requirement of the equations. The mathematical framework that underlies our entire current model of cosmology, known as Lambda-CDM, is built on a metric called the Friedmann-Lemaitre-Robertson-Walker metric. This set of equations describes how the universe expands, how matter clusters, and how the Big Bang unfolded over nearly 14 billion years. And these equations only function as written under one condition. The universe must be the same in every direction and in every location. Remove isotropy and the math begins to fall apart. For most of the 20th century, every measurement we made confirmed this assumption. The universe looked smooth. The distribution of galaxies, while locally lumpy with clusters and voids, seemed to average out into a featureless sea at the largest scales. The equations worked beautifully. And then we looked more carefully at the oldest light in existence, and we found something that should not be there. The cosmic microwave background is the afterglow of the Big Bang itself. Roughly 380,000 years after the universe was born, the primordial plasma that filled all of space cooled enough to become transparent. Photons that had been trapped in a constant collision with electrons were suddenly free to travel. They have been traveling ever since, and today, nearly 14 billion years later, they fill the entire sky. Every direction you look, those ancient photons are arriving at your face at this exact moment. They have been redshifted by the expansion of the universe to the point where they fall in the microwave range, invisible to human eyes, but detectable by satellites. When you map the temperature of this background radiation across the full sky, it looks almost perfectly uniform. But almost is doing a tremendous amount of work in that sentence. There are tiny variations in temperature, fluctuations of about 1 part in 100,000, that represent the seeds of structure in the early universe. These were regions where the primordial plasma was fractionally denser or slightly less dense, and from these tiny wrinkles, all the galaxies, stars, and planets we see today eventually grew. To a cosmologist, these fluctuations are a map of the very beginning of time. To study these fluctuations, scientists use a mathematical tool called multipole expansion. Think of the entire CMB sky as a complex piece of music. Multipole expansion is the process of separating that complex sound into its individual notes. Each note corresponds to fluctuations at a different angular scale. The dipole is the simplest note, just showing that one side of the sky appears slightly warmer because our galaxy is moving through space. Scientists remove this contribution immediately because it says nothing about the early universe and everything about our local motion. The next note is the quadrupole. This represents temperature variations on the very largest possible scale, essentially dividing the sky into 4 broad regions of slightly warmer and slightly cooler temperatures. After that comes the octopole, which represents the next level of detail, dividing the sky into 8 broad patches. In the standard model of cosmology, these 2 notes should be completely independent of each other. The quadrupole and the octopole arise from quantum fluctuations that occurred in the first fraction of a second after the Big Bang. These fluctuations were random. The process of cosmic inflation that stretched them to the large scales we observe today should have scrambled any correlation between the orientation of different multipoles. Expecting the quadrupole and the octopole to point in the same direction would be like expecting 2 people in separate rooms, each throwing a handful of dice independently, to produce not just the same numbers but the same geometric patterns with the dice on the table. In 2005, researchers working with data from the Wilkinson microwave anisotropy probe, known as WMAP, sat down to precisely measure the orientation of these 2 multipoles. WMAP was the most advanced instrument of its kind at the time, a satellite positioned at a gravitationally stable point about 1.5 million kilometers from Earth, designed specifically to map the CMB with unprecedented sensitivity. What the researchers found was a statistical anomaly of the first order. The axis of the quadrupole and the axis of the octopole were not at random angles to each other. They were almost perfectly correlated. They were stacked on top of each other, both pointing toward the same specific direction in space. The probability of this happening by chance was calculated to be less than 1 in 1,000. That might sound like enough room for a coincidence, but in physics, a result with a 99.9% chance of being real is not treated as a fluke. It is treated as either a profound discovery or a major experimental error. The cosmologist João Magejo coined the term axis of evil specifically because of how destructive this alignment is to the theoretical framework. If the larger scale structures of the universe have a preferred orientation, the universe is not isotropic. Space has a top and a bottom. It has a direction, and that direction, infuriatingly, appears to align with the plane of our own solar system. When researchers projected this axis onto a map of the sky, they found it sitting almost precisely on the ecliptic, which is the plane of the Earth's orbit around the Sun. The axis also appeared to point toward the equinoxes. This created a logical paradox that was difficult to look at directly. The cosmic microwave background was set in stone 380,000 years after the Big Bang, nearly 14 billion years ago. Our solar system did not even exist until about 4.5 billion years ago. There is no physical mechanism within our standard model by which a pattern, embedded in the fabric of space 9 billion years before the Sun was born, could be oriented with respect to the orbit of a small planet. Around that same Sun, the scientific community's first response was entirely reasonable. They assumed it was a mistake. There were several plausible sources of error, and for years the dominant assumption was that one of these contaminating effects must be responsible for the pattern. The most serious concern was foreground contamination. The CMB maps we see in textbooks look clean and pristine, but that cleanliness is achieved through an intensive data processing step called cleaning. The Milky Way itself sits between us and the CMB, and it is an extremely noisy environment. Our galaxy emits its own microwave radiation from high-speed electrons spiraling through magnetic fields in a process called synchrotron emission. It also emits thermal radiation from the warm dust in star-forming regions. All of this galactic noise has to be subtracted from the raw satellite data before you can see the CMB clearly. If that subtraction is even slightly imperfect, some of the geometry of the Milky Way can bleed into the cosmic data. Because the Milky Way lies roughly in the same plane as our solar system, any leaked galactic signal would naturally appear to be aligned with the ecliptic. It would create exactly the kind of ghost pattern that looks like a cosmic axis, but is actually just the shadow of poorly subtracted dust from our own neighborhood. A second concern was the effect of our own motion. The solar system is moving through space at approximately 370 kilometers per second relative to the CMB rest frame. This produces a large dipole signal. While the dipole is straightforward to remove mathematically, the correction is not perfect, and an imperfect correction can introduce a secondary effect called the kinetic quadrupole, which can distort the larger multipoles and potentially create artificial alignments. There was also the problem of the galactic mask. Because the center of our galaxy is so bright that it completely obscures the CMB behind it, cosmologists have to place a digital mask over that region and simply exclude those pixels from the analysis. When you cut a large hole out of the middle of a dataset, you fundamentally change its statistical properties. Critics of the axis of evil argued that the specific shape of this mask could be distorting the multipole reconstruction in a way that creates a false alignment. This is known as an artifact of the reconstruction process. Finally, there was the statistical argument called the look elsewhere effect. This principle acknowledges that if you examine a large enough dataset for long enough, you will inevitably find patterns that appear statistically extraordinary. The human brain evolved to find patterns, and it finds them even where none genuinely exist. While the alignment with the ecliptic is strange, critics noted that if the axis had instead aligned with the galactic North Pole, or with the path of the Moon, or with the direction of our motion through space, we would have been equally amazed by any of those alignments. The concern was that out of thousands of possible statistical measures, researchers had found the one that looked miraculous and highlighted it. An unconscious form of data selection. These were serious and well-reasoned objections, and the scientific community waited patiently for the next generation of technology to simply make the anomaly disappear. In 2009, the European Space Agency launched the Planck satellite. Planck was a fundamentally different instrument from WMAP. It carried 9 frequency channels compared to WMAP's 5, which meant it could characterize and subtract foreground contamination with vastly superior accuracy. Its detectors were cooled to within a fraction of a degree above absolute zero, giving it a sensitivity to temperature fluctuations roughly 3 times better than its predecessor. If the axis of evil were a product of instrumental bias or imperfect foreground subtraction, Planck was almost certainly going to find that out. The first major release of Planck cosmological data came in 2013. Subsequent refined analyses followed in 2015 and 2018. The results were not what many cosmologists had hoped for. The alignment between the quadrupole and the octopole was still there. Planck confirmed it across multiple frequency channels, which meant that the different instrumental channels, each seeing different foreground contributions, all agreed on the axis. If it were a foreground contamination artifact, it should have appeared at some frequencies but not others, or it should have changed depending on which foreground subtraction model was used. Instead, the signal was remarkably consistent across the full range of Planck's capabilities. This confirmation was a turning point. The conversation in the astronomical community shifted. It was no longer sufficient to dismiss the axis as a likely instrument error. Something about the data was real and persistent. The question was what? One of the most powerful tests for distinguishing between a real cosmic signal and a statistical artifact is to look not just at the temperature of the CMB, but at its polarization. The light from the early universe carries information in two distinct forms. The temperature maps, which are the colored sky maps you most commonly see, show tiny differences in the energy of photons across the sky. But those photons are also polarized, meaning they have a specific orientation or twist that was set at the moment they last scattered off electrons in the primordial plasma. This polarization signature, known technically as E-mode polarization, is a completely independent measurement. It is generated by a different physical process at the same moment in cosmic history. If the axis of evil is a genuine property of the early universe rather than a statistical fluke or a systematic error, it should show up equally clearly in the polarization data as it does in the temperature data. If the alignment only exists in the temperature measurements, that would be a strong indication that something is wrong with the temperature maps rather than with the universe. By 2024 and 2025, teams analyzing the Planck polarization maps began publishing their findings. The results were described as frustratingly ambiguous, which in the language of science is a loaded phrase. Some research groups found that the polarization data does show a preferred direction consistent with the temperature axis. This would be deeply significant because it would mean that whatever caused the alignment was present at the physical moment the light was emitted, not introduced later by instrumental effects or data processing. Other groups, however, found that the signal-to-noise ratio in the polarization maps was too low to draw firm conclusions. Because the polarization signal is much weaker than the temperature signal, smaller systematic errors in the data can more easily obscure the true underlying pattern. What this leaves us with is a picture in which the axis of evil has survived every attempt to explain it away as an error, but has not yet been confirmed with the ironclad certainty required to overturn the cosmological principle. It exists in a frustrating scientific middle ground. It is too persistent and too consistent across independent instruments to ignore. It is not yet confirmed across enough independent measurement types to force a theoretical revolution. The most powerful argument for dismissing the axis of evil was always the fact that it appeared in only one data set. Even if something is wrong with the CMB maps, the argument went, a real anisotropy in the universe should show up elsewhere. It should affect the motion of galaxies. It should influence the rotation of large-scale structures. It should leave fingerprints on objects throughout the cosmos. If the universe genuinely has a direction, that direction should be visible in more than just the temperature of ancient light. This argument began to weaken significantly around 2022 and continued to erode through 2024 and 2025 as independent data sets from completely different sources began to point toward the same directional bias. The first of these independent confirmations involves a phenomenon known as dark flow. When photons from the CMB pass through galaxy clusters, they undergo a subtle frequency shift caused by their interaction with the hot gas inside those clusters. This effect, known as the kinetic Sunyaev-Zeldovich effect, allows astronomers to measure the velocity of galaxy clusters relative to the CMB rest frame with considerable precision. Beginning in the late 2000s and extending into the current decade, researchers surveying thousands of galaxy clusters separated by hundreds of millions of light-years made a discovery that defied straightforward explanation. These clusters, spread across an enormous region of sky, appear to be flowing collectively toward a specific patch of the sky at speeds that cannot be accounted for by any known mass distribution within the observable universe. The expansion of the universe does not produce this kind of coherent directional flow. The gravity of visible matter is insufficient to explain it. The prevailing interpretation is that there is some immense mass concentration beyond the edge of the observable universe whose gravitational influence is being felt inside it. This is possible because the gravitational influence of matter propagates at the speed of light, and in the time since the Big Bang, gravity from matter just beyond our observable horizon may have had enough time to set large-scale flows in motion. whatever is causing it, the direction of this dark flow is roughly consistent with the axis identified in the CMB, the same broad region of sky that the CMB anomaly points toward also appears to be the direction in which thousands of galaxy clusters are collectively moving. The second independent line of evidence comes from the study of quasars. Quasars are among the most luminous objects in the universe, the intensely energetic cores of distant galaxies powered by supermassive black holes actively consuming enormous quantities of material. Because they are so bright, they can be detected across billions of light years, making them ideal markers for probing the large-scale structure of the universe. In studies published between 2022 and 2025, astronomers conducting large surveys of quasar populations found something that had no obvious explanation within the standard model. The spin axes of these supermassive black holes are not randomly oriented with respect to each other. Across distances of billions of light years, quasar spin axes appear to be statistically aligned, and the direction of this large-scale alignment is consistent with the axis seen in the CMB data. This is a result that should not exist under our current understanding of physics. There is no mechanism within the standard model by which a black hole formed in one corner of the universe should have any knowledge of the orientation of a black hole formed billions of light years away. They formed from completely independent regions of space, from gas clouds that had never been in causal contact with each other. The only way to produce a coherent alignment over such distances is if both objects were influenced by the same underlying feature of the universe itself, some structural property of space that set a preferred direction during or shortly after the Big Bang and imposed that direction on everything that formed within it. When you combine the CMB temperature anomaly, the dark flow of galaxy clusters, and the alignment of quasar spin axes into a single picture, the statistical probability of all three pointing in the same general direction by chance collapses to something very close to zero. This is what scientists call a multi-messenger signal. We are no longer looking at a single anomaly in a single data set that might be explained by a sensor glitch or a cleaning error. We are looking at a consistent directional bias woven through three completely independent types of measurement. The CMB temperature data was collected by microwave satellites. The dark flow signal was measured using the distortion of CMB photons by galaxy clusters. The quasar alignment was measured in optical surveys of distant active galactic nuclei. These three measurements have essentially nothing in common technically, and yet they all agree. This convergence of independent evidence is what elevates the axis of evil from a curiosity to a potential crisis for modern cosmology. A single anomaly can be a mistake. Three independent anomalies pointing in the same direction, observed through completely different physical mechanisms, are much harder to dismiss. To understand the full severity of what is at stake, it helps to appreciate just how deeply the assumption of isotropy is embedded in our theoretical framework. The standard model of cosmology, Lambda-CDM, is one of the most successful scientific theories ever constructed. The CDM stands for cold, dark matter, the most widely accepted explanation for the invisible gravitational scaffolding that holds galaxies and galaxy clusters together. The lambda stands for the cosmological constant, representing the dark energy that is driving the accelerating expansion of the universe. Together, these two additions to general relativity produce a model that correctly predicts an enormous range of observations, from the large-scale distribution of galaxies to the detailed pattern of temperature fluctuations in the CMB, to the abundance of light elements like hydrogen and helium that were produced in the first few minutes after the Big Bang. But this model rests on a specific set of equations, and those equations require isotropy as a non-negotiable input. The Friedmann-Lemaitre-Robertson-Walker metric, which is the mathematical heart of standard cosmology, is a solution to Einstein's field equations that was derived under the explicit assumption that the universe is both isotropic and homogeneous. Homogeneous means the same in every location. Isotropic means the same in every direction. If either of these assumptions fails, the metric is not applicable as written. This is not a minor technical detail. It means that if the axis of evil represents a real physical anisotropy in the universe, the mathematical foundation of essentially everything we know about the Big Bang, the age of the universe and the expansion history of space is built on a flawed starting assumption. We might be calculating the expansion rate of the universe, the density of matter and energy, and the age of the cosmos, all based on equations that assume a uniformity that does not actually exist. This connects directly to one of the most pressing unsolved problems in modern astronomy, the Hubble tension. The Hubble constant is a number that describes how fast the universe is expanding. For decades, astronomers have been measuring this number, and for decades, they have been getting different answers depending on which method they use. When the Hubble constant is measured by analyzing the detailed pattern of fluctuations in the CMB and extrapolating forward using the standard cosmological model, it comes out to approximately 67 kilometers per second per megaparsec. This means that for every 3.3 million light-years of additional distance between us and a galaxy, that galaxy appears to be moving away from us approximately 67 kilometers per second faster. When the same constant is measured directly, by observing nearby pulsating stars called Cepheid variables to calibrate distances, and then using those calibrated distances to measure the recession velocities of galaxies via type 1a supernovae, the result comes out to approximately 73 kilometers per second per megaparsec. That is a discrepancy of roughly 9%, and as measurements have become more precise over the past decade, the gap has stubbornly refused to close for a long time. The dominant hope was that the tension would be resolved by discovering a systematic error in one of the two measurement chains. Perhaps the Cepheid calibrations were slightly off, or the supernovae were not quite as standardizable as we assumed, or the CMB analysis had a subtle bias. But as the measurements have been refined and checked and cross-validated using multiple independent methods, the tension has only grown. As of the current period, it appears to be a real discrepancy between what the universe is doing, according to direct measurement, and what the standard model predicts it should be doing. Here is where the axis of evil and the Hubble tension connect in a way that many cosmologists find deeply suggestive. In a perfectly isotropic universe, the Hubble constant should be the same in every direction. But if the universe has a preferred axis, if it has some large-scale structure that makes it expand slightly differently in different directions, then the Hubble constant might genuinely vary depending on where you are looking. We might be living in a region of space where the local expansion rate is slightly higher or slightly lower than the global average. If we are using this local expansion rate to calibrate our distance ladders while using the global average embedded in the CMB to predict what the expansion should be, the two numbers will never agree no matter how precise our measurements become. In this framework, the axis of evil and the Hubble tension are not two separate anomalies. They are two symptoms of the same underlying disease, a universe that is not as uniform as our model requires it to be. The axis is the directional evidence for non-uniformity. The Hubble tension is the quantitative evidence that the expansion of space is not behaving the same way everywhere. Together, they suggest that Lambda-CDM is not wrong in the sense of being completely incorrect. It is likely still a very good approximation for many purposes, but it may be an oversimplification of a more complex reality, a smoothed-out average of something that is genuinely lumpier, more structured, and more directional than the model allows. There is one aspect of the axis of evil that is particularly philosophically uncomfortable, and that is its alignment with our own solar system. It is not just that the universe appears to have a preferred direction. It is that this preferred direction appears to be tied to the orbital plane of the Earth around the Sun and to the positions of the equinoxes. This is the part that strains credulity most severely, because there is no physical connection between the large-scale structure of the universe and the local geometry of our solar system. For scientists, the most obvious resolution to this discomfort is foreground contamination, as discussed earlier. The ecliptic is the plane along which most of the interplanetary dust in our solar system orbits the Sun. This dust, called zodiacal dust, glows faintly in the infrared and microwave bands. If the CMB maps have not perfectly subtracted this local foreground, a ghost of the solar system's geometry could be imprinted on the cosmic maps. The ecliptic alignment of the axis would then be telling us not about the universe, but about our failure to fully clean the data. This is the preferred explanation of most mainstream cosmologists, and it is a compelling one. The alternative is something that modern physics has spent 4 centuries trying to move away from. If the axis is real and the alignment with the solar system is genuine, it suggests in some sense that our location in the universe is not ordinary. It suggests that we are not in a random, unremarkable corner of an isotropic cosmos, but in a place that is somehow connected to the architecture of the whole. Some theorists have proposed that this could be explained if we live inside or near a large cosmic void, a region of space that is significantly less dense than the cosmic average. In a void, the way light propagates and the way the local geometry of space is curved would be slightly different from the global average. This could create local anisotropies that have nothing to do with a global preferred direction in the universe, and which would naturally appear to align with whatever local geometry is present, including the plane of our solar system. The void hypothesis has genuine scientific support. There is evidence that we may indeed live in a somewhat underdense region of space. The KBC void, named for the researchers Keenan, Barger, and Cowie, who characterized it in 2013, is a proposed large-scale underdensity in the local universe with a radius of several hundred million light-years. If this structure is real and if we sit near its center, it could potentially explain both the apparent Hubble, tension, and some aspects of the axis anomaly as consequences of local rather than global anisotropy. But accepting this explanation comes with its own philosophical cost. If we are near the center of a large underdensity, our location is not random in the way the Copernican principle requires. We are not in an average place. We are in a special place, the center or near center of a significant cosmic structure. This does not bring us back to geocentrism in any meaningful physical sense, but it does mean that using our local observations to infer the global properties of the universe is more complicated than the standard model assumes. The Copernican principle, in its strongest form, does not just say that we are not at the center of the solar system. It says that our observations of the universe are typical, that a random observer placed anywhere in the cosmos would see roughly the same universe we see. If we are in a special location, that stronger claim fails, and much of our cosmological methodology depends on the stronger claim being true. This is why the axis of evil is philosophically as well as scientifically troubling. It is not just about one unusual alignment in one dataset. It is about whether the fundamental observational strategy of cosmology, the assumption that what we see from Earth represents a fair sample of the universe as a whole, is valid. If our standard assumptions are failing us, what might replace them? This is where theoretical physicists have been most creative, and the range of proposed explanations is remarkable. The most conservative explanation is called non-trivial topology. In the standard cosmological model, the universe is assumed to be infinite in extent, or at least so large that it is effectively infinite for any practical purpose. In a truly infinite flat universe, there is no reason for any direction to be preferred. But what if the universe is finite and has a specific geometric shape? A universe shaped like a 3 torus would be finite in all 3 dimensions, but would have no edge. If you travel far enough in any direction in a toroidal universe, you would eventually return to where you started, just as a person walking on the surface of a sphere eventually circumnavigates it. In such a universe, light from the Big Bang would travel around the shape of space and arrive at our position from multiple directions. The geometry of the torus would impose a preferred structure, on the largest scale temperature patterns because the torus is not symmetric. If it is shorter in one dimension than another, the largest fluctuations would naturally align along the shorter axis. Simulations published in 2025 showed that a specific toroidal topology for the universe could reproduce the quadrupole and octopole alignments seen by Planck with remarkable fidelity. This is intriguing because it requires no new physics. Toroidal topology is fully consistent with general relativity. The universe can be finite and topologically non-trivial without violating any known physical laws. The challenge is that we have no other direct evidence for this topology, and there are theoretical arguments against the universe being small enough for its topology to be observable. A more radical proposal involves replacing the geometric framework of general relativity itself. General relativity is built on what mathematicians call Riemannian geometry. In this framework, the properties of space, the way distances are measured, and the way paths curve through space-time are the same regardless of which direction you are facing. This directional neutrality is what produces an isotropic universe in general relativity. Finsler geometry is a more general mathematical framework that relaxes this assumption. In a Finslerian universe, the metric tensor that defines distances in spacetime is allowed to depend on direction. This means that the speed of light or the strength of gravity could vary slightly depending on orientation. These differences would be extraordinarily small in our local region of space, too small to have been detected by any existing experiment. But integrated over cosmic distances and cosmic time, they could produce exactly the kind of large-scale anisotropy we observe. A Finslerian universe would have a grain to it, a fundamental directionality built into the vacuum of space itself. The axis of evil would not be a mistake or an artifact. It would be the first observational detection of this intrinsic cosmic grain. While this proposal is speculative, it is mathematically rigorous, and its predictions are in principle testable with future observations of the CMB and large-scale structure. The most speculative, but perhaps most intellectually exciting proposal connects the axis of evil to the holographic principle. The holographic principle, which emerged from theoretical work on black holes and quantum gravity in the 1990s, proposes that the information content of a three-dimensional region of space can be fully encoded on its two-dimensional boundary. In the context of cosmology, this suggests that our entire three-dimensional universe might be a projection of information encoded on a two-dimensional surface at the edge of space. If this is correct, the properties of that boundary surface could influence the appearance of the three-dimensional universe projected from it. Just as a hologram produces a three-dimensional image that is always oriented in a specific way relative to the reference beam that created it, a holographic universe would have a preferred direction determined by the structure of its boundary. The axis of evil in this interpretation would be the observational signature of the boundary surface from which our universe is projected, detectable in the oldest light we can see because the projection was established at the beginning of time. This idea gained some traction in theoretical discussions in 2025, partly because it provides a natural way to connect the large-scale axis to the local alignment with the solar system. If the holographic projection has a specific center or reference point, and if our solar system is located near that reference point due to some structural feature of the projection, then an alignment between the cosmic axis and local astronomical features would not be coincidental. It would be expected. A fourth theoretical direction involves primordial magnetic fields. In the first tiny fraction of a second after the Big Bang, the universe was far hotter and denser than any state we can currently reproduce in a laboratory. Under these conditions, it is possible that a coherent magnetic field permeated all of space. Magnetic fields are by their nature directional. They have a north pole and a south pole, and they impose a preferred axis on any charged plasma they permeate. If the early universe was threaded by a strong primordial magnetic field during or shortly after inflation, this field could have aligned the quantum fluctuations of the early plasma along a specific direction. The resulting temperature fluctuations in the CMB would preserve this alignment to the present day. The same field, or its remnant influence, would also have shaped the formation of the first galaxies and galaxy clusters, potentially explaining the large-scale alignment of quasar spin axes and the directional flow of galaxy clusters. The primordial magnetic field hypothesis is attractive because it provides a single physical cause for multiple independent observations. It requires no exotic geometry, no modifications to general relativity, and no reference to quantum gravity. It operates within the known physics of electromagnetism and plasma dynamics, applied at extreme conditions in the early universe. All of these theoretical proposals share a common quality. They are attempting to explain the axis of evil within a framework that remains fundamentally scientific and testable. None of them require the universe to have been designed with us in mind. None of them require abandoning the scientific method. They are all, in different ways, attempts to identify a physical feature of the cosmos that our current model has overlooked. What they collectively suggest is that the standard model of cosmology, despite its remarkable successes, is an approximation. It is a model that works very well at the scales where it has been tested, but may be missing important physics at the very largest scales. The axis of evil is a signal that those largest scales are not as well understood as we thought. The current era of cosmological research is characterized by a growing tension between the precision of our observations and the adequacy of our theories. On one side, we have instruments of extraordinary sensitivity producing measurements of unprecedented accuracy. The Planck satellite mapped the CMB with a precision that would have seemed impossible a generation ago. Ground-based observatories like the Dark Energy Survey and the Atacama Cosmology Telescope have mapped the large-scale structure of the universe in increasing detail. The Vera Rubin Observatory, coming fully online in the current decade, will survey half the sky repeatedly for 10 years, building up a map of galaxy positions and motions of unparalleled scope. On the other side, we have a theoretical framework that was built on simplifying assumptions made when the data available to cosmologists was far less precise. Lambda-CDM was constructed in an era when the errors in our measurements were large enough that small deviations from isotropy and homogeneity were invisible. As those errors have shrunk, deviations that were previously hidden below the noise floor have begun to emerge. The axis of evil is the most prominent of these emerging deviations, but it is not the only one. The Hubble tension is another. There are also anomalies in the distribution of matter at intermediate scales that current simulations using Lambda-CDM do not perfectly reproduce. There are peculiarities in the clustering of galaxies that require increasingly baroque modifications to the standard model to explain. Individually, each of these anomalies might be a statistical fluke or a systematic error. Collectively, they paint a picture of a model that is being pushed to its limits. This does not mean that everything we know is wrong. The Big Bang happened. The universe is approximately 13.8 billion years old. Dark matter exists in some form. Dark energy is driving an accelerating expansion. These conclusions are supported by multiple independent lines of evidence and are not seriously contested. What is being questioned is the level of detail in our model. Lambda-CDM is almost certainly a first-order description of reality that captures the dominant features while smoothing over subtleties. The axis of evil is one of those subtleties making itself heard. The next generation of observations will be decisive. The Simons Observatory, a collection of microwave telescopes currently under construction in the Atacama Desert of Chile, is designed specifically to measure the polarization of the CMB with a sensitivity far beyond anything achieved by Planck. Its primary scientific goal is to detect B-mode polarization, a specific signature of gravitational waves from the Big Bang that would confirm the theory of cosmic inflation. But as a byproduct of this search, it will also produce the most detailed CMB polarization maps ever made. If the axis of evil is a real physical feature of the universe, these polarization maps should show it clearly and unambiguously. The polarization of the CMB is generated by a physical process fundamentally different from the temperature fluctuations. Foreground contamination affects temperature and polarization differently. If the axis appears consistently across both with the same orientation, the case for it being an artifact evaporates. If it disappears or changes character in the polarization data, the case for it being a real cosmic feature becomes untenable, and we will need to rethink our foreground models. Similarly, the Vera Rubin Observatory's legacy survey of space and time will map billions of galaxies across a significant fraction of the sky over the course of the current decade. This will produce a three-dimensional map of the large-scale structure of the universe of sufficient density and extent to directly test whether the universe is isotropic at the scales where we currently see the CMB anomaly. If the distribution of galaxies shows the same preferred direction as the CMB axis, the case for a real cosmic anisotropy will be essentially airtight. If the galaxy distribution is perfectly isotropic while the CMB shows an alignment, that tension itself will be highly informative. The LIGHT-BIRD satellite, developed through a collaboration between the Japan Aerospace Exploration Agency and international partners, including NASA and ESA, is planned for launch in the late current decade. LIGHT-BIRD is specifically designed to measure large-scale CMB polarization from space, where it will be shielded from many of the systematic effects that ground-based telescopes face. It will directly address the polarization confirmation question for the axis of evil with a level of rigor that current instruments cannot achieve. Within the next decade, we will almost certainly have a definitive answer. Either the axis of evil will be confirmed as a robust feature of both temperature and polarization data, at which point the cosmological community will face a genuine crisis and a theoretical revolution will be required, or it will dissolve in the polarization data, revealing itself as a subtle but pervasive systematic error in our temperature maps, and our confidence in the standard model will be somewhat restored, though the Hubble tension will remain unsolved. What is remarkable about this situation is how it encapsulates the scientific process at its most fundamental level. Science advances not by confirming what we already know, but by confronting the places where reality disagrees with our expectation. The axis of evil is one of those places. It has been confronted, examined, prodded, and challenged for over 2 decades. It has survived every attempt to explain it away. It has been seen by multiple independent instruments. It has been corroborated by independent measurements in completely different parts of the electromagnetic spectrum, using completely different astrophysical objects, and it remains, stubbornly and uncomfortably, pointing at us from the oldest light in the universe. Whether it turns out to be the greatest systematic error in the history of observational cosmology or the first clear signal that the universe has a direction, the process of investigating it has already taught us an enormous amount. It has revealed the limits of our foreground cleaning methods. It has exposed the sensitivity of our statistical conclusions to the assumptions built into our analysis pipelines. It has forced cosmologists to think carefully about the distinction between what the universe is actually doing and what our model predicts it should do. The axis of evil has made cosmology a more careful and more self-aware discipline. It has forced the field to grapple with questions about the foundations of the standard model that might otherwise have been left unexamined for another generation. In that sense, regardless of how the story ultimately resolves, it has already been scientifically valuable. There is something deeply affecting about the situation we find ourselves in. We built our most successful theory of the universe on the assumption that we are nobody special, that our corner of the cosmos is as ordinary as any other, that the laws of physics and the distribution of matter look the same from everywhere. We made that assumption not out of intellectual laziness but out of humility, out of a principled rejection of the pre-scientific tendency to place ourselves at the center of everything. And now the universe itself may be telling us that this admirable humility, taken to its logical extreme as a mathematical assumption, may not be precisely correct. Not because we are physically at the center of the universe, not because the cosmos was designed for our benefit, but because the universe has a structure, a geometry, An orientation that is real and objective, and that we happen to be aligned with in a way that is neither predicted nor well understood. This is not a comfortable position for science to be in, but it is an honest one. We are looking at a pattern in the oldest light we can see, and we do not yet know what it means. We have built the most sophisticated instruments in human history to examine it, and it has not disappeared. We have developed theoretical frameworks ranging from the conservative to the extraordinary to explain it, and we do not yet know which one, if any, is correct. The universe is not obligated to be simple. It is not obligated to conform to the mathematical elegance of our models. It has been surprising us at every step of the journey. The cosmic microwave background itself was a surprise. Dark matter was a surprise. Dark energy was a surprise. The accelerating expansion of the universe was a surprise. The axis of evil is the latest in a long sequence of surprises, and there is no reason to think it will be the last. We began this story with a 400-year-old assumption that has served science extraordinarily well. The Copernican principle, the principle of mediocrity, the idea that we are not special. That principle has guided us from the solar system to the galaxy to the large-scale structure of the universe. It has helped us understand the Big Bang and the age of the cosmos and the fate of stars, but science is not about defending assumptions. It is about testing them. And right now, one of our most fundamental assumptions is being tested by something that shows up in the temperature of light that has been traveling toward us since before the sun existed. The answer to that test, when it finally comes, will tell us either that our instruments were fooling us in a way we did not anticipate, or that the universe we thought we lived in is not quite the universe we actually live in. Either outcome would be one of the most significant results in the history of astronomy. And either way, the journey of finding out will have pushed our understanding of the cosmos further and deeper than it has ever been pushed before. If you find yourself wanting to follow along as this story develops, as new polarization data arrives from the Simons Observatory and the Light Bird satellite, as the Vera Rubin Observatory maps billions of galaxies across the sky, as theorists continue to refine and test their proposals for what the axis might mean, then staying engaged with the science as it unfolds is exactly the right response. The greatest scientific detective story of the current era is still in progress, and the evidence is still coming in. Subscribing to updates from the people tracking this research is the best way to be there when the answer finally arrives. The cosmic microwave background is the oldest photograph we have of the universe. For most of its history, that photograph looked like noise, beautiful random noise that confirmed our deepest assumptions about the simplicity and uniformity of space. Then we looked more carefully, and in the oldest light in existence, we found something that looks remarkably like a compass needle. Whether that needle is pointing toward a deeper truth about the geometry of the universe, or toward a subtle error in the way we read our own instruments, is the defining scientific question of this moment in cosmology. We are no longer passive observers of a random sea of stars. We are detectives, examining the oldest evidence in existence, trying to determine whether the universe we thought we understood is the universe that actually exists. The answer is out there, written in the polarization of ancient light, in the motion of galaxy clusters, in the spin of black holes separated by billions of light years. We just have to be precise enough, careful enough, and humble enough to read it correctly. To understand how far our understanding of the CMB has come, it helps to appreciate the full arc of discovery that brought us to this point. The cosmic microwave background was not discovered by a scientist deliberately searching for the afterglow of the Big Bang. It was stumbled upon accidentally in 1964 by two radio astronomers named Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories in New Jersey. They were attempting to calibrate a large horn-shaped antenna for use in satellite communications, and they kept finding an annoying, persistent noise in their detector that they could not get rid of. The noise was the same in every direction they pointed the antenna. It did not correlate with the time of day, the season, the position of the sun, or any known local source of interference. At one point, they even considered the possibility that the noise was caused by pigeons nesting in the antenna and leaving deposits on the receiver. They cleaned out the birds, cleaned out the deposits, and the noise remained. It was uniform, isotropic, and relentless. Meanwhile, at nearby Princeton University, a theoretical group led by Robert Dicke was preparing to search specifically for the cosmic microwave background. Dicke's team had worked out the theory: if the universe began in an extremely hot, dense state and had been expanding and cooling ever since, the afterglow of that primordial heat should still fill the universe today, redshifted into the microwave band. They were about to begin building their detector when they received a phone call from Penzias and Wilson. The two groups quickly realized they were describing the same phenomenon from opposite directions, one as an inexplicable experimental nuisance and the other as a theoretically predicted signal. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for the discovery. But the CMB in 1964 was understood only as a uniform background glow. The technology of the time could not detect the tiny temperature fluctuations, those 1 part in 100,000 variations that encode the detailed story of the early universe. The first satellite mission dedicated to mapping these fluctuations was the Cosmic Background Explorer, launched by NASA in 1989. COBE, as it was known, produced the first full-sky maps of the CMB temperature variations and confirmed their basic statistical properties. The lead scientists of the COBE mission, George Smoot and John Mather, received the Nobel Prize in Physics in 2006. COBE was succeeded by WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. WMAP produced maps of the CMB with roughly 40 times better angular resolution than COBE, allowing astronomers to see the fine structure of the temperature fluctuations in detail for the first time. It was WMAP data that first revealed the axis of evil in 2003, when scientists Dominic Schwartz, Craig Coppey, Dragan Hutera, and Glenn Starkman published their analysis of the multipole alignment anomaly. This was the paper that set off 2 decades of debate, analysis, counter-analysis, and theoretical speculation. The history of how we built instruments to see the CMB is itself a story of extraordinary technical achievement. The temperature of the CMB is approximately 2.73 degrees Kelvin above absolute zero. The fluctuations we are trying to measure on top of that background are about 100 millionths of a degree in amplitude. To detect variations this small against a background this cold, CMB satellites carry detectors that must be cooled to temperatures lower than anything that exists naturally in deep space. The Planck satellite's highest frequency detectors operated at a temperature of 0.1 degrees Kelvin, colder than any naturally occurring region in the observable universe. The full technical story of how engineers built instruments that can measure temperature differences of 100 millionths of a degree from a satellite sitting 1.5 million kilometers from Earth, while correcting for the thermal emissions of the satellite itself. The radiation from the Milky Way, the thermal dust from solar system objects, and the subtle frequency-dependent effects of our own atmosphere is itself a testament to the extraordinary sophistication of modern experimental physics. It is against this backdrop of extraordinary technical achievement that the persistence of the axis of evil is most remarkable. These instruments were not built by careless experimenters. They were built by teams of thousands of engineers and scientists who spent decades thinking about every possible source of systematic error. The Planck mission alone involved contributions from more than 40 institutions across 15 countries. The data analysis pipeline that produces the final CMB maps involves hundreds of scientists applying independent methods and cross-checking their results against each other. And despite all of this care, all of this sophistication, all of this independent verification, the axis remains. The specific geometry of the axis deserves more careful examination. When cosmologists describe the CMB as an all-sky map, they are projecting the full sphere of the sky onto a two-dimensional surface, much like how a globe is projected onto a flat map. The standard projection used for CMB maps is called the Mollweide projection. In this projection, the galactic plane, the flat disk of the Milky Way, runs horizontally across the middle of the map and the ecliptic. The plane of the Earth's orbit around the Sun crosses it at a slight angle. When scientists draw the axis of the quadrupole across this map, it runs very nearly parallel to the ecliptic. When they draw the axis of the octopole, it too runs very nearly parallel to the ecliptic. And when they measure the angle between the quadrupole axis and the octopole axis, it comes out to less than 3 degrees. In a universe where these two axes should be randomly oriented relative to each other, the expected separation would be somewhere around 50 degrees on average. Finding them within 3 degrees of each other is already an anomaly. Finding them both aligned with the ecliptic simultaneously is the compound coincidence that makes the whole affair so difficult to dismiss. The ecliptic alignment has a specific quantitative characterization. Astronomers define the ecliptic pole as the direction perpendicular to the plane of the Earth's orbit. The north ecliptic pole sits in the constellation Draco. The angular separation between the CMB axis and the ecliptic plane has been measured to be less than 5 degrees across multiple independent analyses using both WMAP and Planck data. For comparison, the typical angular separation you would expect between a randomly oriented axis and any specific reference plane by pure chance would be about 45 degrees on average. The alignment with the equinoxes adds another layer of specificity. The equinoxes are the 2 points in the sky where the ecliptic intersects the celestial equator. These points shift slowly over time due to the precession of the Earth's axis, but at any given moment they are 2 specific coordinates on the sky. The CMB axis appears to point roughly in the direction of the vernal equinox, the point where the Sun appears to cross the celestial equator on its way north in spring. This is not just alignment with a plane, this is alignment with a specific direction within that plane. The compound probability of both alignments occurring by chance is extremely small. The equinoctial alignment is significant because it further reduces the number of possible astrophysical explanations. Foreground contamination from the galactic plane might conceivably align the axis with the ecliptic because galactic emission is distributed along a plane similar to the ecliptic. But the equinoxes are not associated with any known source of electromagnetic emission. There is no known physical reason why a foreground contamination effect would produce an alignment that is specifically oriented toward the equinoctial direction rather than simply toward the ecliptic plane in general. This is what makes the axis of evil so scientifically interesting and so difficult to classify. It is not just a broad anomaly. It is a precisely specified alignment that shows multiple simultaneous correlations with the local geometry of our solar system. Each additional specificity makes it harder to explain as a chance coincidence, but each additional specificity also makes it harder to identify a plausible physical mechanism that could produce it. The broader context of CMB anomalies is worth exploring because the axis of evil does not stand entirely alone. There are several other features of the CMB maps that have attracted attention over the years as potential deviations from the predictions of the standard model. The most famous of these is the cold spot, a region in the southern sky near the constellation Eridanus that is significantly colder than the surrounding CMB temperature. The cold spot is roughly 2 billion light-years across and represents one of the largest known structures in the observable universe in terms of angular extent on the sky. Various explanations have been proposed for it, including a supervoid, a region of lower than average density through which CMB photons would lose energy as they travel, a cosmic texture left over from a phase transition in the early universe, and more speculatively, a signature of a parallel universe in a multiverse scenario. The cold spot is interesting in the context of the axis of evil because it sits in the southern galactic hemisphere, roughly in the direction that the axis points. If both features are caused by the same underlying large-scale structure of the universe, they may be different symptoms of the same anisotropy. Some theoretical models that produce a CMB axis also predict associated temperature anomalies in specific regions of the sky, and the cold spot is roughly consistent with some of those predictions. There is also the observed asymmetry in the amplitude of fluctuations between the two hemispheres of the CMB sky. In a perfectly isotropic universe, the variance of temperature fluctuations should be the same in every direction. Statistical analyses of both WMAP and Planck data have found that the fluctuations are slightly stronger in one hemisphere of the sky than the other. The dividing line between the two hemispheres is oriented roughly consistently with the axis of evil. This hemispheric power asymmetry is another anomaly that the standard model has difficulty explaining, and it appears to be correlated directionally with the multipole alignment. The lack of power at the largest angular scales is a third anomaly. In the standard model, the CMB should have a certain amount of temperature variance at very large angular scales, corresponding to the quadrupole and the lowest multipoles. The observed power at these scales is consistently lower than the model predicts. The axis of evil anomaly is partly a consequence of this lack of power, because a universe with less large-scale power overall also tends to show the remaining large-scale power concentrated in a specific direction rather than spread uniformly around the sky. These three anomalies, the axis alignment, the cold spot, and the hemispheric power asymmetry, have been characterized independently and through different analytical methods, yet they appear to be correlated with each other directionally. They all seem to favor the same broad region of sky as anomalous. This directional correlation between independent anomalies is part of what makes the overall picture concerning. If these were truly independent statistical flukes, the probability of them all pointing in the same direction would be very small. The theoretical implications of a non-isotropic universe extend beyond cosmology into particle physics. The standard model of particle physics, which describes the fundamental forces in particles with extraordinary precision, is also built on the assumption of Lorentz invariance, which is the principle that the laws of physics are the same in every direction and at every velocity. Lorentz invariance is closely related to isotropy. If the universe has a preferred direction at cosmological scales, some theorists argue that it might also imply a subtle violation of Lorentz invariance at smaller scales, though the universe could plausibly be anisotropic at large scales while remaining Lorentz invariant locally. Searches for Lorentz violation have been conducted using a variety of high-precision experiments, including atomic clocks, particle accelerators, and gamma-ray observations of distant astrophysical sources. The most sensitive tests come from examining the behavior of cosmic rays and gamma rays arriving from different directions to see if their properties depend on the direction they come from. So far, these tests have found no evidence of Lorentz violation to extremely high precision. But the precision of these tests applies to the local physics of high-energy particles, not to the large-scale structure of the universe. It is possible for the cosmos to have a preferred direction at billion light-year scales while remaining locally isotropic to the precision measurable by current experiments. The connection to inflation is perhaps the most theoretically significant aspect of the axis of evil. The theory of cosmic inflation, first proposed by Alan Guth in 1980 and subsequently developed by André Linde and others, proposes that the very early universe underwent a period of exponential expansion during which space itself expanded by at least a factor of 10 to the power of 26 in an extraordinarily brief interval. This expansion stretched quantum fluctuations from subatomic scales to cosmic scales and is responsible for seeding the large-scale structure we observe today. One of the key predictions of the simplest inflation models is that the universe should be very close to perfectly flat and very close to perfectly isotropic. The rapid expansion during inflation smooths out any pre-existing anisotropies or curvatures, just as inflating a wrinkled balloon smooths its surface. If inflation was very long, the observable universe we see today is an infinitesimally small patch of the post-inflation universe, and any large-scale structure that existed before or during inflation would be smoothed to unmeasurability. The axis of evil poses a challenge to this simple picture. If the CMB truly has a preferred direction, inflation either did not smooth things out as thoroughly as the simplest models predict, or the preferred direction was generated by the inflation process itself, or it was generated by some physical process that occurred after inflation ended. Some modified inflation models, including those with anisotropic initial conditions, or those in which inflation proceeds differently in different directions, can produce large-scale anisotropies in the CMB, but these models are more complex than the simplest inflation scenarios and require additional justification. The axis of evil is, therefore, not just a challenge to the standard model of cosmology. It is potentially a challenge to our understanding of the very earliest moments of the universe, the period during which the seeds of all structure were planted by quantum fluctuations stretched to cosmic scales. If those seeds were not perfectly random and isotropically distributed, we need to understand why. Dark energy, the mysterious component of the universe that is driving the accelerating expansion, adds another layer to this story. In the standard model, dark energy is represented by the cosmological constant, a fixed energy density that is the same everywhere in space and the same in every direction. But there is no fundamental theoretical reason why dark energy has to be isotropic. Alternative models of dark energy, sometimes called dark energy quintessence or dynamical dark energy, allow for a dark energy field that varies in space and time. If dark energy is not isotropic, it could contribute to the observed large-scale anisotropy in the CMB. Dark energy field that is slightly stronger or slightly weaker in different directions would affect the rate of cosmic expansion in those directions and would leave an imprint on the CMB temperature fluctuations. Some researchers have proposed that the Hubble tension, the axis of evil, and the observed large-scale bulk flows of galaxy clusters might all be connected through an anisotropic dark energy field that has a preferred orientation in space. This proposal is speculative, but it has the virtue of connecting multiple anomalies through a single physical mechanism. If dark energy is anisotropic and has the same axis as the CMB alignment, it would explain why we see consistent directional biases in so many different types of observations. Testing this proposal requires precise measurements of the dark energy equation of state in different directions of the sky, which is an extremely challenging observational task, but one that future surveys may be able to accomplish. The concept of a multiverse provides another theoretical framework within which the axis of evil might be understood, though it remains highly controversial. In eternal inflation, the process that drives inflation never truly ends everywhere. Instead, it continues indefinitely in most of space, occasionally giving birth to pocket universes like our own when inflation ends locally. Each pocket universe would start with slightly different physical conditions, potentially including different large-scale topologies and different orientations of cosmic structure. In a multiverse context, the axis of evil might be a consequence of a collision between our pocket universe and another one early in its history. Such a collision would deposit energy asymmetrically and could imprint a preferred direction on the CMB. It would also potentially create features like the cold spot. This collision hypothesis gained some attention when early analyses seemed to show a slight temperature anomaly at the boundary of the cold spot that could be consistent with a cosmic bubble collision. However, subsequent analyses have been inconclusive, and the multiverse collision hypothesis remains speculative. The relationship between the axis of evil and our understanding of time is subtle, but worth exploring. In the standard model, the universe had a beginning in the Big Bang, and the direction of time, what we experience as the arrow of time, is a consequence of the universe starting in an extremely low entropy, highly ordered state and evolving toward higher entropy. The CMB is the most direct evidence we have for this initial low entropy state, because its near-perfect uniformity represents an extraordinary degree of order that was present at the beginning. If the universe has a preferred spatial direction, as the axis of evil suggests, it might also have implications for the arrow of time. Some theoretical frameworks that attempt to explain large-scale spatial anisotropy also predict a subtle asymmetry in the time evolution of the universe, a difference in the properties of the universe in the temporal forward and backward directions that goes beyond the simple statistical arrow of time arising from entropy. These ideas are highly speculative, but they illustrate how deeply the implications of a cosmological anisotropy could reach into our fundamental understanding of physics. The practical consequences of a non-isotropic universe for observational astronomy are worth considering. Most of our astronomical distance measurements rely on the assumption that objects of a given intrinsic brightness appear dimmer with distance according to the inverse square law in a uniform isotropic space. If space is not isotropic, the relationship between distance and apparent brightness would vary with direction. This means that our entire cosmological distance ladder, built on the consistency of type 1a supernovae, Cepheid variable stars and other standard candles, might have systematic directional errors embedded in it if the universe is expanding slightly faster in one direction than another, as the axis of evil hypothesis suggests might be possible. Then the calibration of the distance ladder would give different results depending on which direction the objects you are calibrating against happen to lie. Some researchers have pointed out that the specific samples of supernovae and Cepheids used to measure the local Hubble constant are not uniformly distributed across the sky. If these samples happen to be preferentially located in one directional hemisphere rather than the other, and if the expansion rate is different in different directions, this could contribute to the Hubble tension. This connection between the axis of evil and the Hubble tension through the distribution of calibrating objects on the sky is not just speculative. Several research groups have specifically examined whether the Hubble tension depends on the direction in which it is measured. The results so far are suggestive but not conclusive. There appear to be some directional trends in the measured Hubble constant, with slightly different values obtained from supernovae samples in different parts of the sky. But the uncertainties are large enough that the results are not yet definitive. If the next generation of surveys, with their much larger samples of supernovae and Cepheids spread more uniformly across the sky, reveals that the measured Hubble constant depends on the direction in which you look, that would be one of the most significant confirmations of the axis of evil as a real physical feature of the universe. And it would simultaneously explain the Hubble tension as a consequence of living in an anisotropic universe, measuring the expansion rate in a limited directional sample that does not fairly represent the whole. The philosophical implications of this entire enterprise deserve to be stated clearly. Science is the systematic process of revising our understanding of reality in response to evidence. The history of cosmology is a history of revisions, each one revealing that the universe is stranger, larger, older, and more complex than previously understood. The Copernican revolution moved us from the center of the solar system. The recognition that the Milky Way is just one of many galaxies moved us from a privileged position in the cosmos. The discovery of the CMB placed us firmly within a universe with a defined history and a finite age. The axis of evil, if it is real, represents the next revision in this sequence. It would not tell us that we are at the center of the universe in any literal sense, but it would tell us that the universe is not as symmetric and featureless as we assumed, that it has structure at the largest scales we can see, and that understanding that structure requires new physics beyond what we currently have. Every major revision in our understanding of the cosmos has led to new technologies, new mathematical frameworks, and new ways of seeing. The discovery of dark matter led to new theories of particle physics. The discovery of dark energy led to new models of the vacuum energy of space. The discovery of the CMB anisotropy axis, if it holds up, will lead to new theories of cosmic topology, new modifications to general relativity, or new models of the very earliest moments of the universe. Whatever the axis of evil ultimately turns out to be, it has already served a crucial scientific function. It has forced us to confront the assumptions that undergird our most successful theories. It has reminded us that our mathematical models are tools we use to describe nature, not nature itself. And it has demonstrated once again that the universe is not obligated to be as simple as we would like it to be. The next several years will see this story develop rapidly. The Simons Observatory will begin full science operations in the current decade. The Lightbird satellite will follow. The Vera Rubin Observatory will accumulate years of survey data. The CMB Stage 4 experiment, an ambitious ground-based initiative involving multiple observatory sites across the globe, will push polarization sensitivity to levels that the present generation of instruments cannot match. All of these experiments are converging on the question of whether the universe has a preferred direction. They are approaching it from different angles, using different physical effects, different wavelengths, and different populations of cosmic objects. The answer they return will be one of the most consequential scientific results of the current generation. If the axis dissolves, we will learn something profound about the systematic errors that can afflict our measurements of the oldest light in existence, and that knowledge will make future CMB science more robust. If the axis persists and polarization confirms it, we will know that the universe has a secret written into its geometry from the very beginning. And that secret will be the defining puzzle of cosmology for the next generation of scientists. We find ourselves, as we so often do at the frontier of physics, standing at the edge of what we know, looking out into a territory that our maps do not yet describe. The cosmic microwave background is the oldest map we have, drawn by the universe itself in the moment when it first became transparent to light. And in the corner of that map, there is something that looks like an annotation we did not expect to find, a marking that suggests the map has a north, and that we have been sailing without quite knowing it. Whether we discover that the marking is an artifact of the cartography or a genuine feature of the territory, the journey of finding out is precisely the kind of journey that defines what science is. It is the process of asking the universe to tell us what it is, and listening carefully enough to hear the answer, even when that answer challenges everything we thought we knew. The axis of evil remains the most prominent unsolved anomaly in modern cosmology. It is written in the oldest light we can see. It has survived 20 years of scrutiny. It has appeared in independent measurements from independent instruments looking at independent physical phenomena, and it is pointing, with uncomfortable precision, in our direction. The universe has been trying to tell us something since before our sun was born. We are finally building the instruments precise enough to hear it. What it says when we do will be among the most important words in the history of human understanding. There is a dimension of the axis of evil's story that rarely receives the attention it deserves, and that is the human dimension. The scientists who discovered this anomaly did not set out to upend cosmology. They were doing careful, methodical work on the statistical properties of the CMB, the kind of painstaking analysis that occupies most of a researcher's career without producing headlines. When the alignment first appeared in their calculations, the initial reaction was not excitement. It was doubt. The assumption was that something had gone wrong in the analysis, and the months that followed were spent searching for the error. This experience is characteristic of how science actually works at the frontier. The dramatic narrative of a scientist having a sudden flash of insight and immediately recognizing a great discovery is the exception rather than the rule. More commonly, a researcher finds a result that looks wrong, spends considerable time trying to prove it wrong, and only gradually accepts that it might be real when the error refuses to materialize. The history of the axis of evil is in many ways the history of an anomaly that scientists have been trying to explain away for 20 years without success. João Magejo, who coined the term axis of evil, was already known in the cosmological community for his willingness to challenge conventional wisdom. He was a co-developer of the theory of varying speed of light, an alternative to inflation that proposed that the speed of light was much higher in the very early universe. This kind of theoretical adventurousness is not common in physics, where careers are built on careful adherence to established frameworks. Magejo's choice of the provocative term, axis of evil, for the CMB anomaly reflected both his personality and his genuine conviction that this was not a minor statistical footnote, but a signal of something deeply wrong with the standard model. The naming itself became part of the story. The choice of language from geopolitics was intentional and slightly provocative, a way of communicating the severity of the challenge. In the community of cosmologists, the name stuck, not because it was dramatic, but because it was accurate. This alignment is evil in the technical sense for the equations. It violates the symmetry that those equations require. And the fact that a name chosen for its rhetorical impact accurately describes the mathematical situation has made it one of the more memorable coinages in recent astrophysical literature. The peer review process for the original axis of evil papers was itself eventful. Reviewers initially raised many of the same objections that the broader community subsequently debated: foreground contamination, galactic masking, the look elsewhere effect. The authors addressed these objections in their revisions, but the papers were accepted with the understanding that they were presenting a statistical anomaly that required further investigation rather than a definitive discovery. This is how science is supposed to work. The papers were careful to frame the result as a puzzle rather than a conclusion, and the community treated it accordingly. The response from the WMAP team itself was notable. The official WMAP science papers acknowledged the quadrupole-octopole alignment as an anomaly, but attributed it to possible foreground contamination and statistical coincidence. This cautious institutional response reflected the natural tendency of large scientific collaborations to be conservative in their interpretations. The WMAP team had invested enormous effort in producing the cleanest possible CMB maps and were understandably reluctant to endorse an interpretation that suggested their data was contaminated in a previously unrecognized way. Their caution was scientifically appropriate. The anomaly warranted further investigation, not immediate acceptance as evidence for new physics. The subsequent history illustrates the scientific method operating across a timescale of years and even decades. Different teams performed independent analyses using different statistical methods and different foreground subtraction approaches. Some found the anomaly slightly less significant when they changed the galactic mask or used a different foreground model. Others found it equally significant regardless of the specific choices made in the analysis. The weight of evidence gradually accumulated in the direction of the anomaly being robust, culminating in the Planck confirmation. Understanding the significance of the Planck confirmation requires understanding what Planck actually did differently from WMAP. The fundamental challenge in CMB cosmology is separating the signal of interest, the temperature fluctuations of the primordial background, from all the other sources of microwave emission in the sky. Planck's approach was to observe the sky at 9 different frequencies simultaneously. The CMB signal has a very specific frequency spectrum that is the same in every direction. Foreground emissions from the galaxy, from galaxy clusters, and from the solar system each have their own characteristic frequency spectra that are different from the CMB. By measuring the total signal at multiple frequencies and using the known spectral properties of the foregrounds, Planck could separate the components much more accurately than WMAP. The fact that the axis appeared consistently across multiple frequency channels in Planck data is therefore a powerful statement. If the axis were caused by imperfect subtraction of the galactic foreground, it should appear prominently in the channels where galactic emission is strongest and be absent or weaker in the channels where it is weakest. Instead, the axis was found with consistent statistical significance across channels spanning the full range of frequencies Planck observed. This multi-frequency consistency is one of the strongest arguments that the axis is not a foreground artifact, the discussion of foreground. Contamination would be incomplete without addressing one specific and subtle effect called the integrated Sachs-Wolf effect. As CMB photons travel through the universe from their point of origin to our detectors, they pass through regions of varying density. When a photon enters a region that is denser than average, it gains energy falling into the gravitational well. When it exits the other side, it loses energy climbing back out. In a universe with constant dark energy, these two effects exactly cancel. But in our universe, where dark energy is causing space to expand at an accelerating rate, the gravitational wells are shallower when the photon exits than when it entered, because the accelerating expansion has partially stretched the well away. This means the photon exits with slightly more energy than it had when it entered, producing a slight warming in the CMB in the direction of massive galaxy clusters. This integrated Sachs-Wolf effect operates over the entire line of sight from the Big Bang to us, and it correlates the temperature we see in the CMB with the distribution of matter in the relatively nearby universe. Some researchers have argued that because the largest superstructures in the nearby universe are not perfectly isotropically distributed, the integrated Sachs-Wolf effect could be creating or enhancing the CMB anomalies we observe. The axis of evil would then be, in this interpretation, a reflection of the large-scale structure of the matter distribution in our cosmic neighborhood, an imprint of the clustering of galaxies across billions of light-years on the oldest light in the universe. This is actually one of the more scientifically interesting proposed explanations, because it would connect the CMB anomaly directly to the observed distribution of matter. If the Sunyaev-Zeldovich dark flow of galaxy clusters and the CMB axis are both reflecting the same large-scale structure through different physical channels, that would represent a coherent physical picture in which the anomaly is real but local rather than cosmological. It would not require modifying the fundamental assumptions of cosmology. It would require a large-scale matter distribution that is more asymmetric than the standard model predicts, which is itself interesting and scientifically important. The question of what constitutes a discovery in physics is illuminated by the axis of evil's story in a particularly clear way. In particle physics, there is a well-established convention that a result is considered a discovery when it exceeds a statistical significance of 5 sigma, meaning the probability of the result occurring by chance is less than about 1 in 3.5 million. This extremely high threshold is set because particle physics experiments look for anomalies in enormous amounts of data, and the look elsewhere effect, the accumulation of statistical flukes in large data sets, is a serious concern. In cosmology, the situation is different and in some ways more difficult. There is only one universe to observe, and the CMB is a single data set. The look elsewhere effect still applies within the CMB data because there are many possible anomalies one could search for, but it applies in a more limited way. When an anomaly is identified, it can be tested against independent data sets, such as the comparison between WMAP and Planck, and against independent types of observations, such as the comparison between temperature and polarization. The axis of evil has passed these tests better than most CMB anomalies. It has been seen by 2 independent satellites and appears in multiple types of data from each. But it has not reached the threshold of certainty that would force the community to conclude definitively that it reflects new physics, rather than a subtle, systematic effect. The resolution of this situation requires either a much more precise measurement of the CMB polarization axis than currently available, or an independent confirmation from a completely different class of observations with better statistical power than the current dark flow and quasar alignment results. Both of these are expected to arrive within the next decade from the instruments currently under development. It is worth considering what it would mean for cosmology if the axis of evil is ultimately confirmed as a real feature of the universe. The implications would be felt not just in theoretical physics, but in the entire practice of observational cosmology. If the universe is not isotropic at the largest scales, every measurement we make of cosmological parameters needs to be qualified with a directional dependence. The Hubble constant is not a single number, but a directional function. The dark energy equation of state might vary with direction. The distribution of matter is not statistically the same in every direction, but has a preferred structure. This would require a comprehensive program of remeasuring and reinterpreting essentially all of our cosmological data. Every survey of galaxies, every measurement of supernovae, every analysis of CMB features would need to be redone with the anisotropy taken into account. The standard fitting procedures, which assume isotropy and homogeneity and fit all sky data to a single isotropic model, would need to be replaced by more complex analyses that allow for directional variation. The good news is that all of these remeasurements and reinterpretations would be scientifically productive. They would not simply correct our existing knowledge, they would generate new knowledge revealing the detailed structure of the cosmic anisotropy and providing new constraints for theoretical models. The scientific community would have a decade or more of highly productive work, characterizing the nature and extent of the anisotropy and using it to distinguish between competing theoretical explanations. The bad news is that some of our most confidently held cosmological results might need to be revised. The age of the universe, currently estimated at 13.8 billion years, is derived from the Hubble constant and the detailed shape of the CMB power spectrum. If the Hubble constant varies with direction and we have been averaging over a non-isotropic distribution of measurements, the derived age might be slightly incorrect. The matter density and dark energy density of the universe, similarly derived from CMB fits and supernovae measurements, might need revision. These would not be corrections of the order of decades in the age of the universe. The existing measurements are sufficiently precise and mutually consistent that the corrections would likely be at the few percent level. But few percent corrections to fundamental cosmological parameters would have cascading consequences for our understanding of the history of cosmic structure formation and the future fate of the universe. If we live in a universe that is slightly but genuinely non-isotropic, the mathematical machinery of cosmology must evolve to match that reality. This is not unprecedented in the history of science. When general relativity replaced Newtonian gravity, the corrections to orbital mechanics and timekeeping at first seemed like small adjustments. But those small adjustments had enormous practical consequences, from the precession of Mercury's orbit to the accuracy of GPS satellites. Small corrections to fundamental frameworks can have outsized practical implications. The axis of evil stands at the boundary between what we know and what we do not. On one side of that boundary is the standard model of cosmology, one of the most successful scientific theories in history, precise in its predictions, validated by an enormous range of observations, and built on the assumption that the universe is uniform at the largest scales. On the other side of that boundary is a universe that may have a direction, a grain, a subtle but permanent asymmetry built into the fabric of space from the very beginning. Between those two possibilities stands a set of observations that are persistent, consistent, and resistant to easy explanation. The oldest light in the universe is pointing at something. We do not yet know whether it is pointing at an error in our instruments, a subtlety in our mathematics, or a fundamental property of reality itself. But we are building the tools to find out, and within a decade, we will have an answer. The search for that answer is science at its most honest and most human. It is the story of people who built extraordinary machines, made careful measurements, found something unexpected, and spent 20 years trying to understand what it means. Whatever the eventual conclusion, the effort itself represents one of the most sustained and rigorous investigations in the history of astronomy, a collective human attempt to read the oldest writing in the universe and understand what it says. The sky above us is not just a backdrop for our lives. It is an archive. Every photon that reaches our detectors carries information about where it has been and what it has encountered across billions of years of cosmic history. The cosmic microwave background is the oldest layer of that archive, a document written in the first light of a universe that was only 380,000 years old. We have been learning to read that document for 60 years, and we are still discovering what it contains. The axis of evil is, at minimum, one of the most unexpected and one of the most important things we have found in that archive so far. Whether it is a clue to the shape of the universe, a hint of physics beyond the standard model, an artifact of our imperfect reading methods, or something else entirely, it has already changed how we look at the sky and what questions we ask of it. We look up, and the oldest light in existence looks back. And in that ancient light, written across the full width of the observable universe, there is something that looks very much like a direction. We do not yet know where it is pointing, but we are getting closer to finding out. The scale of the cosmic microwave background as a scientific tool is worth sitting with for a moment. When we map the CMB, we are not looking at a single object or a single region of space. We are mapping a spherical shell around us that is approximately 46 billion light-years in radius. This number seems larger than the age of the universe in light-years would suggest, and the reason is that space itself has been expanding throughout the time those photons were traveling. The photons were emitted from matter that was then only about 42 million light-years away, but that matter has since been carried by cosmic expansion to its current distance of approximately 46 billion light-years. Every direction we look in the CMB, we are seeing a different region of the early universe. The temperature fluctuation we see in one direction represents the density of the primordial plasma at one point in space, and the fluctuation we see in the opposite direction represents the density at a completely different point, separated from the first by distances of tens of billions of light-years. These two points were not in causal contact with each other when the CMB was emitted. Light had not had time to travel between them. The fact that they look similar to each other is itself one of the great mysteries of cosmology, addressed by inflation theory but not fully resolved. It is against this backdrop of incomprehensible scale that the axis of evil must be understood. The alignment we observe is not between objects that are close together. It is between the temperature structure of the universe on scales of tens of billions of light-years in one direction and the orbital plane of the Earth around the Sun, which is a structure roughly 1 billion kilometers across. The ratio of these scales is approximately 1 quadrillion to 1. The fact that there appears to be any relationship between features at these two scales, whether through a genuine physical connection or through a systematic measurement error, is extraordinary in either case. If the alignment is an error, it means that a measurement error replicated across two independent satellite missions and multiple independent analysis pipelines has introduced a bias that precisely mimics the geometry of the solar system at the quadrillion to 1 scale ratio. This would be a remarkable failure of experimental physics, sophisticated in its specificity and deceptive in its consistency. If the alignment is real, it means that the universe contains a physical feature that connects its largest observable scales to the local geometry of our solar neighborhood in a way that is entirely outside the predictive scope of our current theories. Neither option is comfortable. Both would be significant. Together they define the stakes of the axis of evil problem. The cosmological community has been living with this discomfort for over 2 decades. In that time, careers have been built on studying CMB anomalies. Graduate students have written doctoral dissertations analyzing different aspects of the axis. International conferences have been convened specifically to discuss the implications of the quadrupole-octopole alignment and the related anomalies. The problem has generated hundreds of published papers, ranging from detailed instrumental analyses to speculative theoretical explorations, and the pace of publication on the topic has not slowed. This sustained scientific attention is itself evidence of the anomaly's importance. In a field where new discoveries arrive constantly and the literature is vast, a specific anomaly that continues to attract serious research attention 2 decades after its identification has proven itself to be genuinely difficult and genuinely interesting. If the axis of evil had been easily explained away, the community would have moved on. The fact that it has not been explained away means it continues to demand explanation. The sociological dynamics of a scientific community confronting an anomaly of this magnitude are interesting to observe. There is a natural conservatism in science, a preference for explanations that do not require abandoning well-tested frameworks. This conservatism is, on balance, a feature rather than a bug. The history of science is full of anomalies that were eventually explained within the existing framework, and it contains far fewer cases where a single anomaly required the complete overthrow of a successful theory. So when an anomaly appears, the default scientific response is to look for explanations within the existing framework before invoking new physics. This is what the cosmological community has been doing with the axis of evil for 20 years. But there is also a cost to excessive conservatism. If an anomaly is real and does require new physics, delaying the recognition of that reality also delays the development of the new theories needed to explain it. The history of science also contains cases where anomalies were dismissed or ignored for too long, slowing scientific progress. The tension between appropriate skepticism and openness to new ideas is one that every scientific community must navigate, and the CMB anomaly community has been navigating it in public for a generation. The current situation, as of the middle of the current decade, is one of productive tension. The evidence has accumulated to the point where the simplest explanations, instrument error, and obvious foreground contamination are increasingly untenable. But the evidence has not yet accumulated to the point where a specific theoretical alternative has been confirmed. This is the most scientifically productive moment in the life of an anomaly, the period when it has survived the easy tests but not yet passed the definitive ones. It is during this period that theoretical creativity is most valuable. The proposals being developed now, the toroidal topology models, the Finslerian gravity theories, the holographic projection interpretations, the primordial magnetic field hypotheses, are being refined and tested against the data. The theories that survive the next round of observations will be the ones that predicted specific features of the polarization data or the galaxy distribution that are subsequently confirmed. The theories that fail to make accurate predictions will be discarded. This is the mechanism by which science converges on truth. Not through authority or consensus, but through the progressive elimination of theories that disagree with nature. The role of the axis of evil in the broader crisis of modern cosmology deserves to be stated clearly. We are at a moment in the history of cosmology when the standard model is under greater observational pressure than at any previous time in its history. The Hubble tension is real and has not been resolved. The sigma-8 tension, a discrepancy between the predicted and observed clustering of matter at intermediate scales, is real and unresolved. The axis of evil is real and unresolved. Several anomalies in the distribution of large-scale structure at the edges of the observable universe are real and unresolved. Taken individually, each of these could be a measurement error or a statistical fluke. Taken collectively, they form a pattern. They are all pointing toward the same conclusion, that the standard model of cosmology, while capturing the dominant physics of the universe, is missing something at the edges of its applicability. The model was built for a universe that is perfectly uniform, perfectly smooth, and expanding uniformly in every direction. The universe we are observing, with its tension in the Hubble constant and its axis in the CMB and its clustering anomalies, is telling us that this perfect uniformity is an approximation rather than a truth. Understanding the nature of this approximation is the central challenge of cosmology for the coming generation. It will require new theoretical frameworks, new observational strategies, and new ways of thinking about the relationship between local physics and cosmological physics. The axis of evil is the most prominent landmark in this new scientific territory. It is the anomaly that has been studied longest, confirmed most thoroughly, and connected to the most independent lines of evidence. Whatever its ultimate explanation turns out to be, the axis of evil has already played an important role in pushing cosmology toward greater rigor and greater openness. It has forced the community to think carefully about assumptions that were previously taken for granted. It has highlighted the importance of testing cosmological models in multiple independent ways, rather than relying on a single type of observation. And it has kept open the possibility that the universe is more structured and more interesting than our models allow for the scientists who will spend the next decade analyzing the polarization, maps from the Simons Observatory, surveying billions of galaxies with the Vera-Rubin telescope, and launching new satellites to map the microwave sky from above the atmosphere. The axis of evil is both a challenge and an opportunity. It is a challenge because it demands that they find either a compelling explanation or a definitive refutation. It is an opportunity because either outcome would be a major scientific achievement. The oldest light in the universe is being measured right now, tonight, by instruments on mountaintops and in orbit, instruments designed by thousands of scientists and engineers over decades, instruments of extraordinary precision aimed at a signal of incomprehensible antiquity. In that signal, written in temperature differences of 100 millionths of a degree, is the story of how the universe began and what it was like before anything we recognize as structure existed. And in the largest features of that ancient story, something is pointing. Whether it is pointing toward a new era of physics or toward the limits of our own perceptual systems is the question. The answer will come. It is being measured right now, and when it arrives, it will be one of the most important sentences ever read by human eyes from the oldest text in existence. If the universe has a direction, we will find it. If the direction is an illusion, we will understand why we were fooled. Either way, we will know more about the cosmos than we do today. And that process of knowing more, of asking better questions and building better instruments and revising our understanding in the light of new evidence is what science is and what it has always been. The axis of evil is a puzzle written in the first light of time. We are the generation that gets to solve it, and the solution, whatever it turns out to be, will reshape how every future generation looks at the sky above them and understands the universe they inhabit. One of the most productive ways to think about the axis of evil is to consider it within the history of unexpected alignments in physics and astronomy, cases where nature revealed patterns that had no place in the prevailing theory of the time. The history of science is populated with moments where the data insisted on a structure that the theory did not predict, and those moments have consistently been the precursors to theoretical advances. Consider the anomalous precession of Mercury's orbit, which was known to Newton's contemporaries and remained unexplained for over 2 centuries. Mercury's elliptical orbit around the Sun rotates slowly over time, and the rate of that rotation, measured in the 1800s, was slightly faster than Newtonian mechanics predicted. The discrepancy was small, about 43 arc-seconds per century, barely more than a rounding error by the standards of the time. Various explanations were proposed, including a hypothetical planet inside Mercury's orbit called Vulcan, but none were satisfactory. The anomaly persisted until 1915, when Albert Einstein demonstrated that his newly developed general theory of relativity predicted precisely the observed precession rate. The small anomaly in Mercury's orbit was not a measurement error or a statistical fluke. It was the first confirmed prediction of general relativity. The axis of evil occupies a structurally similar position in the history of cosmology. It is a small anomaly, statistically significant but not overwhelming, persistent across multiple independent measurements, and resistant to explanation within the current theoretical framework. Whether it will eventually be explained by a minor extension of the standard model or by a revolutionary new theory remains to be seen. But its structural similarity to the Mercury precession anomaly, in terms of its persistence and its resistance to standard explanations, is at least suggestive. The detection of cosmic rays at energies above the Greisen-Zatsepin-Kuzmin limit, sometimes called the GZK limit, provides another instructive parallel. In 1966, two physicists independently predicted that protons traveling through intergalactic space at very high energies would interact with the cosmic microwave background photons and lose energy, creating an upper limit on the energies at which cosmic rays could arrive at Earth from distant sources. For decades, this seemed like a firm theoretical prediction. Then, beginning in the 1990s, cosmic ray detectors reported events at energies above this limit. These ultra-high-energy cosmic rays appeared to violate the GZK prediction. The initial response, predictably, was skepticism. The measurements were difficult and the events were rare. But as the data accumulated over years and across multiple experiments, it became clear that the anomalous events were real. The current explanation, still not fully resolved, involves a more detailed understanding of the sources of ultra-high-energy cosmic rays and the complex processes by which they propagate through space. The GZK anomaly did not overthrow our understanding of cosmic ray physics, but it significantly refined and complicated it. The axis of evil has the potential to play a similar role. It need not require the complete overthrow of Lambda-CDM to be scientifically significant. A revision of the model that accounts for large-scale anisotropy while preserving the core predictions that have been so well confirmed by observation would represent a major advance. It would tell us something important about the initial conditions of the universe, the topology of space, or the physics of the very early universe that the current model glosses over. The physics of the very early universe, the period from the Big Bang to the end of inflation, is the era we understand least well. The energies involved were so extreme that they exceed anything achievable in our most powerful particle accelerators by many orders of magnitude. We cannot perform controlled experiments on this era. We can only read the imprints it left in the cosmic microwave background and in the large-scale structure of the universe. The CMB is the best fossil record we have of the inflationary era. Every feature of the CMB power spectrum encodes information about what happened during and immediately after inflation. The quadrupole and octopole alignments are large-scale features that probe the very largest quantum fluctuations amplified by inflation, the ones that correspond to modes of cosmic variation that span a significant fraction of the entire observable universe. In the simplest models of inflation, these large-scale modes should have the same statistical properties as the smaller-scale modes that are much easier to measure. They should be random, uncorrelated with each other, and isotropically distributed. The axis of evil tells us that at these largest scales, the modes are not random and uncorrelated. They are aligned, and the alignment, if physical, must encode information about the initial conditions of the inflationary era, about the geometry of space before or during inflation, or about some physical process that occurred during inflation that imprinted a preferred direction. The study of these large-scale modes is sometimes called cosmic variance limited cosmology. Because we can only observe one universe from one location, and because the large-scale modes have very few independent realizations in the observed sky, our statistical power to characterize them is fundamentally limited. Even with a perfect measurement of the entire CMB sky, we can only measure about 5 statistically independent realizations of the quadrupole mode. This is why distinguishing between a real alignment and a statistical fluctuation is so difficult at these scales, and why the confirmation from independent data types, such as polarization and dark flow and quasar alignment, is so important. The limited statistical power at large scales also means that some degree of anomaly at those scales is expected. In any sample of only 5 independent measurements, the probability of finding one that looks anomalous is not negligible. The question is whether the specific anomaly we observe, with its precise geometric alignment and its consistency across independent data sets, is within the expected range of random fluctuations or outside it. The current consensus is that it is unusual enough to be worth investigating seriously, but not yet unusual enough to force a definitive conclusion. The polarization measurements that will come from the next generation of CMB experiments will significantly increase our effective statistical power for characterizing the large-scale modes, not by providing more realizations of the quadruple, but by providing an independent check of the temperature result through a physically different observable. If the temperature alignment is a genuine feature of the early universe, the polarization should show a correlated alignment. If the temperature alignment is a systematic error, the polarization should not show it. This is a clean and definitive test, and it is the one that will most likely resolve the debate over the next decade. The detection of gravitational waves from the Big Bang, which is one of the primary scientific targets of the Light-Bird satellite and the Simons Observatory, would also provide a new window on the large-scale structure of the universe. Gravitational waves from inflation would stretch and compress space in a specific pattern, producing what are called B-mode polarization patterns in the CMB. The amplitude of this B-mode signal depends on the energy scale of inflation. If inflation was high energy, the signal would be large enough to detect with instruments of the current generation. If it was low energy, we might need to build still more sensitive instruments. The B-mode signal is interesting in the context of the axis of evil, because if inflation produced an anisotropy in the large-scale structure, it might also produce an anisotropy in the B-mode pattern. A non-standard inflationary scenario that explains the CMB axis might make specific predictions about the amplitude or direction of the B-mode signal that differ from the standard inflation prediction. Measuring the B-mode signal would then be a test not just of whether inflation happened, but of what kind of inflation happened and whether it was isotropic. This is one of the ways in which the axis of evil is driving innovation at the frontier of observational cosmology. The quest to understand the anomaly is pushing the community to build better instruments, to develop more sophisticated analysis methods, and to think more carefully about what different types of CMB measurements can tell us about the early universe. The long-term legacy of the axis of evil, regardless of how the question of its physical reality is ultimately resolved, is already secured. It has been one of the central scientific puzzles of the first 2 decades of the 21st century in cosmology. It has driven significant investments in new instruments and new analysis techniques. It has challenged the community to think more critically about systematic errors and statistical methods. And it has kept open the possibility that the universe is more interesting than the standard model suggests. If it turns out to be a real physical feature, the axis of evil will be remembered as the first discovery of large-scale cosmic anisotropy, one of the most fundamental measurements in the history of cosmology. If it turns out to be an artifact, it will be remembered as the anomaly that drove the development of analysis techniques precise enough to detect and correct for previously unknown systematic effects in CMB measurements. Either way, the scientific community will have learned something important from 2 decades of careful study. The universe does not offer easy answers to those who question it. It demands precision, patience, and an honest accounting of what is known and what is not. The axis of evil has been demanding exactly these things from the cosmological community since it first appeared in the WMAP data over 20 years ago. The community has risen to that demand with extraordinary effort and extraordinary instruments. And the effort is continuing right now as detectors on mountaintops and in orbit accumulate more photons from the oldest light in existence, measuring their temperatures and their polarizations with ever greater precision. Somewhere in those measurements is the answer. It has been there since the universe was 380,000 years old, encoded in the light that has been traveling toward us for nearly 14 billion years. We are reading that ancient message more carefully than we have ever read it before, and soon the message will yield what it contains. Whether it is the story of a universe more complex than we imagined, or the story of the limits of human instrumentation and the ingenuity required to overcome them. Both stories are worth telling. Both stories are worth discovering. And the universe, as it always has, will not tell us which story it contains until we have done the work of asking precisely enough to hear the answer. To appreciate the full stakes of the axis of evil debate, it is worth examining what our picture of the universe would look like if the anomaly is confirmed as genuine cosmic anisotropy. We would be living in a universe that departs from the idealized smooth sphere of the Standard Model and instead possesses something more like an orientation, a subtle but real asymmetry in the distribution of its earliest large-scale structure. This would not be a universe that looks wildly different from the one we thought we inhabited. The galaxies would still be there in their billions. The cosmic web of filaments and voids would still stretch across hundreds of millions of light years. The Big Bang would still have occurred nearly 14 billion years ago. Dark matter would still constitute approximately 27% of the total energy budget, and dark energy would still account for approximately 68%. These aspects of the Standard Model are supported by so many independent lines of evidence that a moderate departure from isotropy at the largest scales would not overturn. Then what would change is the precision and the interpretation of our cosmological measurements. The Hubble constant would need to be remeasured as a function of direction rather than as a single global number. The parameters that describe the power spectrum of the CMB, the amplitudes and spectral indices that encode the physics of inflation, would need to be fitted to an anisotropic model rather than an isotropic one. The age of the universe derived from the combination of these parameters might shift slightly. The detailed history of structure formation, from the first atoms to the first stars to the first galaxies, would need to be recalculated in a framework that allows for the universe to have looked slightly different in different directions. More fundamentally, it would require a new answer to the question of why the universe has this particular direction. In the Standard Model, there is no such question to answer because the universe has no preferred direction. In an anisotropic universe, the preferred direction is a physical property that must have a physical cause. Was it set during inflation? Was it inherited from a pre-inflationary phase? Was it a consequence of the universe's topology? Was it produced by a large-scale magnetic field in the primordial plasma? Each of these possible causes makes specific predictions about other observables, and testing those predictions would drive a new generation of cosmological research. The search for the cause of the anisotropy, if the anisotropy is real, would connect several currently disconnected areas of theoretical physics. Inflationary theory would need to be generalized to include anisotropic models. String theory and quantum gravity, which may be relevant to the pre-inflationary era, would be confronted with new observational constraints. The theory of the quantum vacuum, which underlies the cosmological constant, and dark energy would need to address the possibility of directional dependence. The connections across these theoretical frameworks, forced by the need to explain a single observational anomaly, would drive progress on multiple fronts simultaneously. This is how big anomalies drive science. They are not just puzzles to be solved in isolation. They are cross-cutting challenges that require different specialties to work together, that force theorists to make specific predictions and experimentalists to design specific tests, and that ultimately produce advances not just in the specific area of the anomaly, but in the broader theoretical landscape. The axis of evil sits at the intersection of observational cosmology, theoretical cosmology, particle physics, quantum gravity, and the philosophy of science. Its resolution will require contributions from all of these fields, and its resolution, whenever it comes, will leave all of these fields changed by the process of addressing it. Scientists working in these areas do not think of themselves as participants in a grand historical drama. They think of themselves as people trying to understand a specific, technical, well-defined problem. But from the outside, the effort is extraordinary. The combination of the technical difficulty of the measurements, the theoretical depth of the questions being asked, and the fundamental importance of the underlying issue, whether the universe has a direction, combines to make the axis of evil one of the defining scientific questions of our era. The public engagement with this topic is also worth noting. Among all the anomalies and tensions in modern cosmology, the axis of evil is the one that has most captured the imagination of people outside the scientific community. The name helps. But so does the core concept, the idea that the oldest light in the universe might be pointing in a specific direction, and that the direction it points might somehow be connected to our solar system. This idea resonates because it sits at the boundary between the astronomical and the intimate, between the incomprehensibly large and the personally familiar. The public interest in the axis of evil reflects something genuine about human curiosity. We want to know whether we are typical or special, whether our location in the universe is ordinary or meaningful. The Copernican principle says ordinary. The axis of evil, if real, hints at something more complicated. Not special in the sense of being designed or privileged, but situated in a way that is connected to the structure of the whole. This is a subtle distinction, but it is an important one, and it is the kind of distinction that science is uniquely equipped to make precisely. We live in an era when the instruments of astronomy are powerful enough to ask questions. That would have been considered metaphysical just a generation ago. We can, in principle, measure whether the universe has a preferred direction. We can test whether our location is typical. We can determine whether the laws of physics are the same in every direction at the largest scales. These are not philosophical questions requiring philosophical answers. They are empirical questions that can be addressed with careful measurements and rigorous analysis. The answer to the axis of evil question will not tell us whether there is a meaning or purpose to the universe. It will not tell us whether we are here for a reason or by chance. It will not address the deep existential questions that humans have been asking since consciousness first turned toward the night sky. What it will tell us is whether the universe we inhabit is the uniform, isotropic, featureless void that our standard model describes, or whether it has a direction, a grain, a structure at the largest scales that we are only now beginning to see. That is already a remarkable thing to be on the verge of knowing. We are the generation that might discover whether the cosmos has a north. We are the generation working with the instruments that will answer that question. And whatever the answer turns out to be, the fact that we could ask it, build the machines to answer it, and do the mathematics to understand the answer, is one of the most extraordinary achievements in the long history of human curiosity about the sky. The axis of evil is waiting for us at the frontier of what we know. The frontier is very close now, and crossing it will change how we see everything beyond it.